practical accuracy surrounding mathematical models of the motor effect. Now the inquiry questioned how practically accurate are mathematical models for the motor effect in determining the strength of a magnetic field using the principles of a current carrying conductor within a field. Some brief introduction to key theory. Now within electromagnetism, the motor effect applies to current carrying conductors in magnetic fields. This states that when a current carrying conductor such as a copper wire within this investigation, which would be this, is subject to a magnetic field, evidently the field between two bar magnets in this context, it will experience a force. As such, within this investigation, both experimental and expected magnetic field strength will be effectively determined utilizing the principles of the motor effect by placing a current carrying conductor within a magnetic field, hence assisting in answering the inquiry question. Since force is directly proportional to current, the mass, and thus the force reading on the balance, will increase at a linear proportional rate to current. As such, increasing the current will result in the force due to the motor effect increasing. However, the magnetic field should theoretically remain constant, as the bar magnets utilized remain unchanged throughout. Thus, it is expected that the mathematical model of the motor effect will be highly accurate, comparing to the precise magnetic field probe apparatus. Detailed below is a list of equipment in the correct quantities and measurements required to obtain primary data within this investigation. Now, some key risks of this investigation include the strength of the bar magnet, copper wire, heat produced from the circuit, alligator clips, and the flow of current. Refer to the 3 columns on the right for inherent injuries, precautionary measures, and residual risk level. So for section 1 of the method, position one side of the 48mm bar magnet of unknown polarity near the north pole of the bar magnet of known polarity. Move the two magnets together. If they appear to repel one another, the side of the 48mm bar magnet facing the red half of the color-coded bar magnet is north, as like poles repel. Conversely, if they attract like so, the side facing the color-coded magnet is the south pole. Record this polarity on the 48mm bar magnet. Repeat these steps for the second 48mm bar magnet. Place these two bar magnets on the U bracket, orientated like so. This will ensure that there is a magnetic field between the two bar magnets, thus allowing the motor effect to apply. With section 2 of the method, place the electronic balance on the desk and set up the two retort stands parallel like so. Fix the two retort clamps onto these retort stands. Fix two connecting wires to the retort clamp and connect these to two alligator clips individually. Cut a 15cm sample of 0.8mm copper wire and connect the edges of this to the two alligator clips. Move the U bracket holding the two bar magnets onto the center of the scale. Ensure north is pointing away from the apparatus, with south facing toward. Gather the power pack and place two connecting wires within the DC ports of the pack. Route the connecting wire in the positive terminal of the DC power pack through the rheostat, and place the connecting wires routed on the right hand side of the copper wire in the other end of the rheostat. This will ensure the current flows from right to left, inducing a force down. Place the connecting wire on the left of the retort stand into the 5A port of the DC ammeter. Place the wire attached to the negative terminal of the DC power pack into the negative port of the ammeter. This will ensure the circuit is complete. Set the voltage to 4 volts and the rheostat initially to the highest resistance. Close the circuit and observe the value of current flowing through the circuit. First test should involve a current of 0.5 amps, so adjust the rheostat accordingly. Turn the circuit off once this has been reached and tear the scale. Close the circuit again, ensuring current remains steadily at 0.5 amps, and observe the mass reading on the scale. Record this mass reading in a table once a steady value is evident on the scale, and switch the circuit off once this process is complete. Repeat this process a further 2 times to determine whether results are repeatable to mitigate random errors. Take an average of these results to increase the accuracy. Repeat these steps again. However, instead of current remaining at 0.5 amps, increase this variable every 3 tests by 0.5 amps by altering the resistance of the circuit using the rheostat up to 2.5 amps. Now for section 3 of the method, first determine the weight force using Fw equals mg and plot a graph of force against current, taking a line of best fit. Take the gradient of this linear curve. Thus, to determine the overall experimental magnetic field strength, divide the gradient by the length of the wire. Pair the magnetic probe to a smartphone and place the probe in line with the current carrying conductor. Begin recording and observe values. Stop recording when the fluctuation in value decreases, and record in the table as evidenced here. Determine the percentage error to ultimately deduce the practical accuracy of mathematical models. Now for a reference, here is a table of variables utilized throughout the investigation. Throughout the investigation, a plethora of data was recorded, namely mass readings on the scale. Furthermore, the expected magnetic field strength with the probe was determined, force applied using the scale using mass times gravity, with the mass being the average recorded on the scale in the previous slide. Now from here, an upward trending relationship between force and current was able to be constructed. Now, as expected within the hypothesis, the graph of force against current would generate a linear relationship, indicating that as the current was increased, the mass reading on the balance would too increase at a uniform rate. This is the case when current is passed through a current carrying conductor within a magnetic field. A force is applied, proportional to the amount of current, generating a reading on the balance. This in turn indicates that through the various tests, since the two variables that changed increased through a linear relationship, the magnetic field strength remained constant, as the strength of the bar magnets were unchanged across all tests. As such, the discrepancy between results gathered mathematically and expected field strength using the magnetic probe should be relatively close. Now this can be deduced through mathematical models. First, using the magnetic field probe, which generated a magnetic field strength of 0.0960 Tesla. Experimentally, mathematical models of the motor effect can be utilized. As a force was induced on the copper wire due to the motor effect, and this was read on the electronic balance, which uses the principle of Fw equals mg to determine the mass reading, then force due to the motor effect equals the weight force. So therefore, BIL sine theta equals mg. Therefore, BIL equals mg. Now the gradient of the linear curve demonstrated mass times gravity over current. Therefore, magnetic field strength multiplied by the length of the current carrying conductor in the magnetic field equals the gradient, which equaled 0.005. Therefore, B equals 0.005, which is the gradient, divided by 0.0048, which equals 0.1042 Tesla. Now from here, the percentage error is able to be determined to determine the actual accuracy of the mathematical models. This ended up being 8.54%. Now this result demonstrates the high degree of practical accuracy using the mathematical models of the motor effect. Accuracy is dependent on the design of an experiment, referring to the level of precision in equipment utilized to collect experimental data close to the true value of the variable being measured. In this investigation, accuracy was fairly high, evidenced in the overall relatively low percentage error of 8.54%. This can be mainly attributed to the process of repetition taking the average results of mass recorded on the balance. The process of repetition ensures all random errors or outliers are able to be removed from any calculations, and any discrepancies between results are able to be averaged, which ultimately brings the experimental value closer to the theoretical, thus resulting in a high degree of accuracy, evident within this investigation. However, although percentage error was relatively low, it remained prevalent to a small degree, indicating this investigation was not extensively accurate. This can firstly be attributed to the limits of accuracy with the electronic balance, recorded to 2 decimal places. Since the mass recorded during each test was quite small, often below 1 gram, there was evident uncertainty due to these limits. However, to resolve this issue, using higher currents would have resulted in higher mass readings on the scale, as force is directly proportional to current, thus minimizing the percentage error. Furthermore, the length of the wire through the magnetic field was measured using the length of the magnets, which is 0.048 meters, with a 15 centimeter copper wire connected to the alligator clips on each edge. However, since magnetic fields between 2 bar magnets are non-uniform, the field extends beyond the realms of the 2 bar magnets. Thus, the length through which the copper wire experienced the force was likely larger than recorded, indicating the magnetic field strength calculated experimentally was higher than the theoretical value. However, in hindsight, connecting the alligator clips to the copper wire at the end of the 48mm bar magnets would have ensured the force due to the motor effect would have only extended 0.048 meters rather than an unknown length due to the non-uniform nature of bar magnets. So overall, accuracy of the motor effect's mathematical models was thorough, illustrated through the low percentage error of 8.54%. The degree to which results are able to be obtained consistently entails the reliability of an investigation. This experiment demonstrated extensive reliability, evident through the almost nominal discrepancy between results gathered. This is mainly credited to the fact that human and random errors were eliminated, as all apparatuses utilized within the circuit were dependent on the voltage induced within the circuit rather than human input. As such, the repeatability and consistency between the relationship of force against current was high, evident through a Pearson's correlation coefficient of 0.9986. However, the small level of deviation on the curve reflects the nature of the power supply. When current enters the power supply, it is in the form of alternating current, where the voltage is far too high for a flow of direct current. As such, voltage is stepped down using a secondary coil and rectified to DC. However, when this process of converting AC to DC occurs, there still remain slight ripples in the DC current curve, which results in fluctuations in current, evident visibly with the needle of the ammeter fluctuating when the circuit was closed, thus inhibiting the reliability slightly. However, overall, this investigation demonstrated comprehensive reliability. Validity encompasses the idea of a fair test, or one that investigates the inquiry question. Valid investigations must effectively control all suitable variables and demonstrate a high degree of accuracy and reliability. First, validity was relatively high, as the inquiry question was effectively addressed, whereby the practical accuracy of mathematical models describing the motor effect was determined to be precise, as the investigation demonstrated a high level of accuracy and certainty. Moreover, the inquiry question was able to be further investigated, as results were repeatable and consistent, resulting in a clear upward and reliable trend of the dependent variable of force against the independent of current. Furthermore, all required variable controls were controlled mostly effectively. However, as mentioned previously, current in the power pack was rectified to DC, resulting in slight fluctuations in voltage. However, this skewed the validity only marginally. Ultimately, though, the validity of this investigation was relatively high, as it effectively sought to answer the inquiry question, and all variable controls were maintained throughout. The inquiry question of this investigation sought to determine the practical accuracy of mathematical models surrounding the motor effect. Through collection of primary data at various currents, this process was able to successfully quantify the inquiry question, which ultimately determined the accuracy of mathematical models through the use of percentage error at 8.54%. Therefore, the mathematical models for the motor effect are quite accurate on a practical level, allowing for a mostly precise measurement of the strength of magnets in terms of Tesla, yet still contains some degree of error. Finally, here is a list of all resources utilized within the investigation. Thanks for watching, sir.